Now I'm going to be explaining an important article from Facebook, which is this article in 2019, Explainable Conversational Reasoning with Attention-Based Walks over Knowledge Graphs. So, for example, in our dialogue we say, can you recommend any classic books like Catcher in the Rye? And because it knows the knowledge graph, it analyzes different paths in the knowledge graph so that it could generate a reasonably good question or answer depending on the utterance of the user. For example, because it knows the knowledge graph, it evaluates all of these different paths. And we need not only the path, but also the entities, and especially final entities. So the idea is that we observe that there exists a small subset of walkable patterns within a knowledge graph or a preferred sequence of graph traversal steps, which often leads to more engaging entities or attributes than others. Note also that the walkable degree of each entity varies by dialogue contexts and domains, thus making conventional rule-based or entity-to-entity learning approaches intractable or not scalable for open dialogue with over 1 million candidate facts. So they proposed graph decoder that attends on viable knowledge graph path to predict the most relevant entities of the knowledge graph by associating these paths with the given input context. So this is another way of our associative memory inside our brain. But now it's interesting that it uses a knowledge graph in our brain and associates path to the given input context, path on the knowledge graph. We then build a parallel zero-shot learning that predicts entities in the knowledge graph embedding and ranks entities based on decoded graph path output. So we have two laws. One of them is for that random walk, and also for the final entities, those relevant entities. So this is the total loss that we should minimize. So in fact, entities are those initial knowledge graph nodes, but your utterance, for example, what the user says, your utterance is a sentence. We know how to encode it, so we have a good representation of that. And also we have the dialogue until that time, so it's historical. And by attention, with attention, you can easily encode that. And now, because you know the sentence and the history and also the initial knowledge graph, you combine all of them and you have a very good representation. But this line goes to saying that this is a path in your entities on your path. These are the relations on your path, and you re-rank the entities, and finally you say, for example, the entity drama is more relevant. So X is composed of a set of, this X is set of entities mentioned, and S is surrounding sentence, and D is the dialogue. So just like here, we concatenate three different things, 1, 2, 3. So these are our X. So our X, so all of them is our X. We encode them. So now we know what is X. The other thing is Y is set of entity path and also relation paths, y of entity, y of relation. Just like here, we have entities paths as well as relation path. So now we know what is x, what is y, and we go from x to y. We want to know which path, which entity path maximizes this score. And we can easily represent entities like this. This is like indicator. It says what is the subject, object, and the relation. If they satisfy that indicator value is 1. And we can measure it by this score function. So the input, we aggregate input context from entities, sentences, and dialogues by applying the modality attention, which selectively attenuates or amplifies each modality based on their importance on the task. So it's a linear combination of these concatenated things, and then plus B, and then you give it this nonlinear activation function. So once we get these modalities A, then we can say we can give it a softmax, and this is a linear combination of your X. And X bar is a good context that summarizes everything, all the information from entities, sentences, and dialogue. Remember, we had 3 things: entities, sentences, and dialogues. And so we represent it by X bar here. It's just a linear combination of XM. And so, as I said, we need 2 laws, one for the walk and one for the correct entity at the next turn. And different models could some of the models, like this model, could really predict the entity correctly. The answer is Muller, award one by Muller. But the other models, you see, they couldn't do that. And another example, could you recommend the book by Mark Overstall? And the response is like this. So sometimes a walk is simple, sometimes it's complicated, and but we need the zero-shot relevance score. We compute zero-shot relevance score in the knowledge graph embedding space, thus allowing for robust prediction for knowledge graph entities and domains unseen during training as well. We use this supervised hinge loss for knowledge graph embedding prediction as a choice of that loss. And F here is just a transformation that walks through the knowledge graph and projects a predicted future entity in the knowledge graph embedding. This Y tilde here refers to the embedding of negative samples, randomly sampled from knowledge graph entities, except the ground truth label of instance. And this is because we need a path. A path is a sequence, so we need these sequence-to-sequence models. So you could use anything that like LSTM, GRU, and those things. But we guide the graph decoder with the ground truth walk path by computing the following loss between predicted path in each of Y of entity or relation. And once the model is trained, at each decoding step, we can rank the potential path based on some of their zero-shot relevance and soft attention-based output pass scores. And so this is an example that we want to minimize this walk pass loss and also the predicted entity. So the baselines that they use is, as you know, because a path is like a sequence, they need, as I said, they need sequence-to-sequence model. And they use 3LSTM, encodes each utterance and all of its related facts within one hop from a knowledge graph to retrieve a response from a small predefined sentence bank. They also use extended encoder-decoder, which conditions response generation with external knowledge vector inputs.